Hi guys, Dr. B here. This is Ideal Gas Law, topic 3.4 for AP Chemistry. The objective is to be able to explain the relationship between the macroscopic properties of a sample of gas or a mixture of gases using the Ideal Gas Law. PV equals nRT, stuff like that, which you should know already. There are a couple of laws that help demonstrate or illustrate the relationship of gases and how it responds under certain conditions. So you have Boyle's law. They have an inverse relationship. As pressure increases, the gas volume decreases. So P1V1 equals P2V2. Charles's law, as the temperatures decrease, the volume decreases. So they have a direct relationship. V1 over T1 equals V2 over T2. Gay-Lussac's law is a direct relationship. As the temperature decreases, so does the pressure, assuming the other things stay the same, such as volume and moles. So P1 over T1 equals P2 over V2. Avogadro's law is a direct relationship. As the number of moles of gas increase, the volume increases, so V1 over N1 equals V2 over N2. The ideal gas law, PV equals nRT. It is used to relate pressure, volume, moles, temperature of gas by using a gas constant at a given condition. So P is pressure in atmospheres, V is volume in liters, N equals moles of gas, universal gas constant 0.08206 liter atmospheres over mole Kelvin. Temperature in Kelvin is Celsius plus 273.15. You should see something similar to this stuff on your laminated sheets. The R values can be different. It just depends on what units you have. So if you have liters or torr, you can use the 62.36 liter torr over mole Kelvin, or 8.314 joules per mole Kelvin. 1 joule equals 1 liter kPa. Always check your units to make sure you use the right one so the units will cancel out. The ideal gas formula can be used to solve for the molar mass or density of the gas. The molar mass equals density in grams per liter times R times Kelvin and temperature divided by pressure. Dalton's law of partial pressures. According to Dalton's law, the sum of all partial pressures of each gas in a mixture is equal to the total pressure. So the P total equals the pressure of A, pressure of B, etc. if those are different gases. Partial pressure is often used when gases are collected over water as shown below. The gas is produced, it's heated up, and the water is displaced and the water in the inverted vessel will empty while the gas is collected. This method allows for the gas to be measured and minimizes the amount of room air that contaminates the sample. As the gas travels through the water, it will pick up water vapor, which will contribute to the gas produced. The amount of water vapor that is picked up is a function of the temperature of the gas. It can be subtracted using Dalton's law of partial pressures. When the water is subtracted, the gas is described as dry. Mole fraction. So a mole fraction is denoted by this funky looking X and equals moles of A over total moles. If a mixture is 3.0 moles of O2 and 4.0 moles of H2, the mole fraction of O2 equals 3 moles divided by the total sum, which is 3 plus 4, and that will be 0.43. To find the partial pressure, multiply the mole fraction by the total pressure of the mixture. Partial pressure equals the mole fraction times the total pressure. When heated strongly, solid calcium carbonate decomposes to produce solid calcium oxide. We've seen this before. Anyway, and carbon dioxide gas, as was shown here. A sample of calcium carbonate is placed in a 35-liter reaction vessel from which all the air has been removed. The vessel is heated to 437 degrees Celsius, at which time the pressure of CO2 is 1.00 atm. Calculate the number of grams of calcium carbonate that is used to produce the carbon dioxide gas. So you're trying to find this. You're kind of given the volume, the temperature, a pressure. So we're actually going to use the ideal gas law to somehow do some stoic. So P equals 1.00 atm. Volume is 35 liters. Temperature is 437 degrees Celsius or 710 Kelvin. So P PV equals nRT. You are solving for N right now because you're going to get the moles. So you're going to divide both sides by RT. So PV is a 1.00 ATM. Well, let's do it like that. So what is going on with this thing? 1.00 times 35 divided by, oh, it's being weird. No. Okay. 0.08206 times 710. What the heck? Parentheses. 710. Just listen to my voice. So 1 times 35 divided by that stuff, you should get 0.600 something moles of CO2. Now you're going to do some stoich. So 0.600 moles of CO2 over 1. In 1 mole of CO2, you have 1 mole of calcium carbonate. And 1 mole on the bottom of calcium carbonate. And on the top will be the molar mass, which is 100.09 grams of CaCO3. You do your math. You should end up with, let's see, the smallest number of sig figs we had is the 2 sig figs from the 35. So 60.13 becomes 60 grams of CaCO3. A basketball is left outside in winter, and when the temperature is 2 degrees Celsius, it has a volume of 6.88 liters, and the pressure inside the basketball total is 0.795. How many moles of gas are in a basketball, and what is the partial pressure of oxygen in the basketball? So let's find the number of moles. So we have a temperature of -2 degrees Celsius. We have a volume of 6.88 liters. We have a pressure of, I guess a total pressure of 0.795 atm. PV equals nRT. Solve for N, divide both sides by RT. So 0.795 times 6.88 divided by parentheses 0.08206 times, you want to put that -2 plus 273, so 271 Kelvin. This will equal my moles, 0.795 times 6.88 divided by that denominator. Should end up with 0.246 moles of gas. To find the pressure of just O2 in the basketball, you are going to take the mole fraction. So it would be PO2 equals the mole fraction of O2 times the total P, I guess P total. Ugh, that's ugly. Times P total equals 0.209 times 0.795 atm. I do my math. Oops, 0.795 times 0.209. I end up with 0.166 atm. All right, gentlemen, that's it for now. Let me know if you have any questions. Okay, thanks, bye.